Another property that is determined by the intermolecular forces is the boiling point. Before we can talk about boiling point, we need a little bit of background information. So vaporization is when we take a liquid and it turns into a gas. And this is when there's high energy molecules at the surface that have enough energy to escape those attractive forces, those intermolecular forces. If we increase the surface area, so say we pour the liquid out onto a surface, we have more surface area, which means we have more potential for the molecules at the surface to escape. This increases the rate of evaporation, allows them to escape the liquid and become a vapor. Now, condensation is the reverse process, where some of the molecules in the vapor, because they're colliding with air molecules or container sides, will lose energy through their molecular collisions and get captured back into that liquid. So vaporization is escaping as a gas, condensation is the gas becoming the liquid. So the stronger our intermolecular forces are, the more energy that the molecules need in order to escape that surface. The weaker our intermolecular forces, the less energy they need to vaporize or to escape the surface. And so they'll vaporize faster. Liquids that evaporate very easily, things like gasoline, fingernail polish remover. These are substances that have low intermolecular forces and we call them volatile. If it's something that doesn't evaporate easily, things that tend to be very viscous and have high intermolecular forces like motor oil, these we call non-volatile. They don't easily turn into a gas. If we want to measure the amount of energy that it takes to turn it from a liquid into a gas, we use a quantity called the heat of vaporization. So delta H with a subscript of VAP for vaporization. Sometimes you'll hear it called enthalpy of vaporization, but much more frequently it's referred to as heat of vaporization. Because we have to add energy in order to get things to vaporize or evaporate, this is always an endothermic value, so it always has a positive value. And it is kind of somewhat temperature dependent, and so we will see changes. If we look at an example of water in our table, if we're at the boiling point, our heat of vaporization is lower than if we are at approximately room temperature, because our molecules have more energy and it's easier for them to escape. Now, if we wanted to talk about the heat of condensation, it is the opposite, so a negative sign in front of our heat of vaporization. But we much more frequently focus on the heat of vaporization. In these two figures, the dashed line represents the amount of kinetic energy required to vaporize substance A and substance B. Both of these substances are at the same temperature. Pause the video to figure out which one has the strongest intermolecular forces. The strongest intermolecular forces are going to be the ones that require the most energy in order to get to that threshold, that require the most amount of energy to become a vapor. So in this case, we have a greater distance, larger kinetic energy to turn substance A into a gas, and a slightly smaller amount of kinetic energy to turn in substance B. So in this case, Substance A has the stronger intermolecular forces. In order to continue our conversation about boiling point, we are going to have to address equilibrium. So equilibrium has to do with the changes that are occurring in our container. So in this case, in flask A, our molecules at the surface are just beginning to vaporize into the empty space above. In flask B, some of the molecules are evaporating, becoming vapor, and some of them are losing energy and recondensing, turning back into the liquid through condensation. Now, when those two rates become equal, as we can see in flask C, we call this dynamic equilibrium. So there's no overall gain or loss of material. It doesn't mean that we have equal amounts of vapor and liquid. It just means that they're changing in equal amounts. Vapor pressure is the amount of pressure that is exerted by the vapor when it is in equilibrium with its liquid. And so the weaker the attractive forces are, there are going to be more molecules in that vapor phase. So more are going to be able to escape because we have those weaker attractive forces. The weaker the attractive forces, the higher the vapor pressure is going to be. Means that we have a more volatile liquid. It's going to evaporate faster. You may have experienced this if you've ever spilled fingernail polish remover or acetone onto a surface. You'll notice that that puddle evaporates very quickly. It has weaker attractive forces. If you compare that to water, which has stronger attractive forces, it's going to take longer for it to evaporate. If we start off with a container that is in dynamic equilibrium of the liquid with its vapor above it, and we change the size of the container, the system is going to shift its position in order to relieve or reduce the effects of that change. So if we increase the volume, there's going to be more evaporation that happens in order to fill that additional space with more molecules. More of the substance is going to leave the surface to fill that space. If we decrease our volume, the evaporation is going to slow, but the condensation is going to increase in order to relieve that stress until we get the pressure restored. Not only does changing the volume affect the vapor pressure, so does changing the temperature. As we increase the temperature, it allows a larger number of molecules to be able to escape the surface of our liquid. As a net result, this means that as the temperature increases, the vapor pressure also increases, as we can see by the curves that are drawn for each of these liquids. The small changes in temperature can make big changes in the vapor pressure. If we want to find the normal boiling point, we need to look at 1 atmosphere, which is 760 torr. We see that for diethyl ether, we have a normal boiling point of 34.6 degrees Celsius. This is just over room temperature of about 23 degrees Celsius. Diethyl ether is 2 carbons attached to an oxygen with another ethyl group or 2 carbons after it. So this is a slightly polar molecule, but not nearly as polar as ethanol. And water has even stronger intermolecular forces, which we can see because of its higher boiling point. than ethanol with a boiling point of 78.3 degrees Celsius. If we want to compare these and their intermolecular forces, our intermolecular forces increase across our graph. So what this means is that if we look at 20 degrees Celsius, our vapor pressure for diethyl ether, which has a lower amount of intermolecular forces, is much greater than for ethanol or for water. So our vapor pressure is lower if we have larger intermolecular forces. This means that our ethylene glycol has the strongest intermolecular forces on this graph. In order for a substance to boil, the temperature of the liquid has to reach a point where the vapor pressure is the same as the external pressure. This is when we start to see bubbles that are forming anywhere in the liquid, not just on the surface, because those molecules have enough energy to turn into the gas phase even at the bottom of the substance as opposed to just at the top that we've talked about with our dynamic equilibrium. When this happens, this is what we call boiling. And the temperature at which that vapor pressure equals the external pressure is our boiling point. And we talked about the normal boiling point being at 1 atmosphere. Now this has some interesting consequences because if we have a lower external pressure, that means that it's going to lower the boiling point of the liquid. So if we look at different elevations throughout the world, our boiling point changes. So say we're in Boston, which has an elevation of 20 feet. It is nearly at sea level. The approximate boiling point of our water is 100 degrees Celsius because atmospheric pressure is 1 atmosphere. If we go and we increase the elevation, say we travel to Denver, now we're higher in the atmosphere, which means there's less atmosphere between us and space. The pressure is lower, and our boiling point is lower because of the fact that there is less external pressure. We reach that boiling point quicker. Now, if we want to take this to the extreme and we go to Mount Everest, which is 29,000 feet above sea level, our pressure, because there is much less air between us and space, is about 0.32 atmospheres, and that decreases our boiling point down to 78 degrees Celsius. So the water boils at 78 degrees Celsius on Mount Everest versus 100 degrees in Boston. Now this does have consequences for cooking food, and it may seem counterintuitive, but it takes longer to cook at a higher elevation. And this is because the amount of energy required to denature the proteins, we have to let it sit in that lower temperature water longer in order to reach the same state as we do when the temperature is higher. So if you've ever looked at a package that you received, you may notice that they give you high elevation cooking instructions on some packages, and it usually takes a longer time to cook.